Hi, I'm Dr. Tom Calabrese, and welcome to this first installment of Insights into Computer Science. This week, I'll be discussing the limitations of natural language as it pertains to problem specification and ways to help us create precise specification statements. The English language is a rich and beautiful language that allows us to express ourselves in so many different ways. According to the 20-volume Oxford English Dictionary, there are 171,476 words in current use, 47,156 obsolete words, 9,500 derivative words, for a grand total of 228,132 possible words to choose from. When we speak, write, send an email or a text, it's important that we choose our words carefully, lest we can cause confusion and send the wrong message. Many words are imprecise, like the infamous four-letter words: fast, slow, nice, soon, near, good, well, easy, or hard. Each of these means something different from the perspective of the person considering it. I may think I'm fast if I race a bunch of 5-year-olds around the yard, but would be pretty slow in comparison to Usain Bolt. But while he is fast compared to me, he would seem like he's standing still compared to something powered by a jet engine. So let's try and avoid using words that are imprecise. Other words may deflect or soften the meaning of what we have to say. A word like prevarication or canard may sound nice, but in fact, you're calling someone a liar. This can cause confusion because these are unfamiliar words and others may not really understand what you mean. In fact, most people have the working vocabulary of a 6th grader. And most people with an advanced education use only about 5,000 words in their vocabulary. So let's keep it simple when choosing our words. So what does this all have to do with problem solving and computer science, you might ask? Well, it turns out that it's super critical. The first step in the problem solving process is creating specifications. A specification is a statement that defines a problem space so that users and implementers can agree on what the program or solution is precisely supposed to do. It describes the nature of the problem that we're trying to solve. For most people, the idea of formulating a specification is really difficult. So here's a trick. Concentrate on the constraints and the criteria that are connected with the problem. Criteria are the solution goals. What has to be done, the outcomes, the things that the program should do. Constraints are the limitations or boundaries that are placed on the problem space. These are things that limit or create boundaries that create the scope of the problem and subsequently bound the solution. These criteria and constraints must be very specific. This is because languages of computer science are so extremely precise. For example, the C programming language contains no more than 100 native commands. Compare this to the 228,132 words in the English language, and it's easy to see why we have to choose our programming words and specification words very carefully. Programming language terms include things like if or while or for. They use assignment statements to set specific values, and because of the small number of terms in a programming language, each action is small and ultra precise. Meaning, a phrase in English like solve for X may translate into 20 lines of C code in that language. That all being said, you should try to express yourself in terms of these computer language words. For example, say things that are phrased as if, then, else for a decision sequence. For example, if the car exceeds 70 miles an hour, then remove your foot from the gas, else keep accelerating. Use Boolean logic to connect conditions and form more precise statements. So for example, if it is raining and my speed is greater than 40 miles per hour, then use the high wiper setting. Next, consider what a program will not do. A constraint like the problem will not consider tax rates from the West Coast states keeps us from doing lots of unnecessary work. Finally, do not assume that the presenter of the problem or owner of the problem has given you all the information that you need to solve the problem. They may not actually have a clear idea of what they want. Clarify, don't make assumptions, and ask questions. Okay, so I think it's time that we work through the specification of a problem by way of example. Suppose that you're asked to create a program that calculates the correct tax and tip for your dinner tab. Sounds easy enough, but is it? When you think about this for a second, there are many unknowns. So first, a little research. According to the Emily Post rules on tipping, a 15 to 20% tip on the pre-tax food portion of your bill is considered customary. All beverages are tipped at $1 per drink, as is customary when tipping the bar staff. So, the criteria for the tip portion of the solution suggests that our program should yield 6 amounts: 15, 16, 17, 18, 19, and 20% increments for suggested tips. We require the input of the amount of the food portion of our bill into our program. So let's call that variable FD_AMT. We need the count of the total number of drinks ordered, and we'll call that variable number DK_NUM. This yields the correct Emily Post formula for the tip, expressed as tip equals the tip percent times FD_AMT. That value will add to it the number DK_NUM. Criteria for the tax portion of our solution is just a little more complicated. In this case, we need the combined value of our food and beverage amount. Let's call that TOT_cost_FB. We also need a tax rate, depending on where you are. We will need to acquire tax tables for all 50 states and the major cities that require an additional city tax. Our solution will need to perform a lookup and set the combined, if applicable, tax rate and assign it to the variable TX_RT. So our formula for total tax is tax equals TX_RT times TOT_cost_FB. But hold on, not so fast. We do have some constraints to consider. First, the tip is computed before the tax. Second, soft drink refills do not count in the number DK_num calculation because you typically don't tip on refills for soft drinks. Third, we need to specify which cities count as major cities, and we will use the AAA definition to accommodate that constraint. Once we've built our table, it's clear that we have quite a bit more information to work with than we did with our initial one-sentence problem description. So in conclusion, one can see that using this simple set of rules can help us be so much more precise in specifying our problem, which of course is going to lead to a much better solution. I hope to see you again in future episodes of Insights into Computer Science, where we'll talk week after week about lots of different and interesting topics that computer scientists think about all the time. Thanks, and see you next time.